Millions of electric vehicle batteries built during the first major wave of EV adoption are approaching the end of their operational lifespans. The default industry assumption is that all of these spent packs will be routed uniformly into standard chemical recycling infrastructure. But recent engineering research from Carnegie Mellon University shows this uniform approach is mathematically and economically flawed. While these massive black boxes look identical on the outside, their internal chemical architectures, primarily LFP, NMC, or NCA, dictate vastly different end-of-life behaviors. Processing all retiring batteries through a single pipeline wastes critical materials, destroys recycler profit margins, and undermines the domestic supply chain. The battery industry is split between two dominant cathode designs: layered oxides like NMC and NCA, and olefins, specifically LFP. LFP has rapidly grown to capture nearly 50% of the global market. Any viable end-of-life protocol must process massive volumes of both chemistries. The ultimate fate of an EV battery, whether it should be shredded for raw metals or repurposed for the national power grid, was locked in the day it rolled off the assembly line. To build an optimized national supply chain, we must implement a chemistry-aware routing protocol. We have to connect the atomic-level structure of the cathode to the macro-level economics of recycling. This is a 3D model of the NMC layered metal oxide structure. These smooth, horizontal pathways allow lithium ions to move highly efficiently. This layered geometry produces high voltage and high energy density. However, it is structurally fragile. Over time, nickel ions migrate out of place and block the lithium pathways. This process, known as cation mixing, causes irreversible lattice degradation. As a result, NMC and NCA cells typically degrade to their 80% state of health threshold after 1,000 to 2,500 charge cycles. Now look at the lithium iron phosphate, or LFP, cathode. This is an olivine crystal lattice. It forms a tightly bound, interlocking three-dimensional network of iron, phosphorus, and oxygen atoms. The extremely strong covalent bonds within this lattice make it highly resistant to structural distortion and thermal runaway. These physical properties allow LFP batteries to comfortably sustain 3,000 to 5,000 full charge cycles, with advanced variants exceeding 6,000. The physical geometry of the cathode permanently dictates the battery's lifespan. It trades raw energy density for extreme physical endurance. These distinct electrochemical behaviors create vastly different economic realities when a battery retires. This table compares the end-of-life recovery value of the two chemistries. The black mass extracted from NMC packs has an average recovery value of €2,045 per ton. This high profitability is driven directly by the presence of scarce transition metals, specifically cobalt and nickel. Hydrometallurgical recyclers extract and sell these metals at a premium. By contrast, LFP black mass yields an average recovery value of just €409 per ton. The LFP cathode is composed entirely of abundant iron and phosphate. It contains no valuable transition metals. Traditional recycling facilities rely on the revenue from recovered cobalt and nickel to cover their massive energy and chemical costs. They cannot process LFP feedstock profitably without charging substantial gate fees or relying on government subsidies. We can construct a logic framework from this data, the battery retirement matrix. We start with NCA packs. Because NCA degrades rapidly but holds immense chemical value, its optimal route is destructive shredding. Recyclers use a technique called acid-deficient leaching to extract these metals economically, requiring fewer reagents and producing less acidic waste than standard methods. This intense chemical refinement is the only way to meet stringent European Union regulations, which require new batteries to contain specific percentages of recycled cobalt, lithium, and nickel. NMC packs sit in the middle ground, requiring state-of-health triage. We split their path at a 70% health threshold. Heavily degraded NMC goes straight to the shredder. Packs that retain a higher capacity can be routed into limited secondary applications before their eventual recycling. For layered oxide chemistries, destroying the physical battery to harvest its chemical components is the only mathematically sound pathway to extract value. Applying this logic to the rapidly expanding volume of retiring LFP packs produces a path that completely bypasses the shredder. Because LFP's material recovery value cannot cover the cost of the chemicals required to dissolve it, direct chemical recycling destroys economic value. But a retired LFP battery removed from a vehicle typically still retains 70 to 80% of its original energy capacity. The optimal route is second life repurposing in stationary grid storage, bypassing the need for physical breakdown entirely. LFP's inherent lack of thermal runaway risk and thousands of remaining charge cycles make it the perfect architecture for grid-scale peak shaving and solar energy shifting. Unlike NMC, the ultimate value of an LFP battery is realized by preserving its physical structure and maximizing its lifespan. This displaces the need to build new batteries for the power grid. Executing this matrix faces an immediate industrial hurdle. Battery packs are permanently sealed, making it impossible to visually determine their internal chemistry or exact state of health on a sorting floor. Without precise internal data, sorting facilities cannot effectively route the packs. To solve this, emerging regulations in the European Union are driving the implementation of a standardized battery passport. This requires digital traceability and rapid diagnostic tools. When a pack arrives at a facility, operators will instantly verify its chemistry and cycle history. Data transparency provides the mandatory bridge between theoretical chemistry and real-world industrial sorting. When we view the flow of these materials on a national scale, the economic stakes become clear. A monolithic recycling policy compounds failures across the supply chain. Shredding LFP packs bankrupts recyclers, while wasting healthy NMC packs places unnecessary strain on primary mining operations. Executing a chemistry-aware matrix directly offsets foreign critical mineral dependencies. High-value NMC and NCA packs are routed into domestic refining hubs to feed new gigafactories. Simultaneously, durable LFP packs are deployed to buffer and stabilize the domestic power grid. To achieve a resilient, circular energy economy, we have to move past the illusion of the universal battery pack and treat the specific chemistry inside.